Okay, so hello everybody, my name is Matteo Marini and this talk will be about efficient detection of use-of-uninitialized memory errors while fuzzing. So, first of all, what are use-of-uninitialized memory or UUM errors? Let's take a look at this code, for example, that attempts to read 4 bytes from standard input. Then it compares the first byte with some magic value, and if they match, it prints hello world. But what if nothing is read? What if the read function fails and it fails to read? Well, in that case, the a variable in the if statement would be uninitialized, but still the conditional branch would be evaluated, and so we would have a use of uninitialized memory error. These kind of errors often cause non-deterministic issues that are very difficult to debug and to detect without the use of specific tools like sanitizers. To detect these kind of tools, we indeed have this kind of errors. We have to use specialized tools like sanitizer, and the workflow to detect this kind of errors is as follows. We first need to define a shadow memory, as it happens with other sanitizers, that contains the initialization status of every other memory region. Then we need to propagate this shadow memory until we reach sensitive operations like pointer dereferentiation or conditional branches. When we do, we check the shadow memory, and if we are using, we detect that we are using uninitialized data, we raise an error. You may wonder why we need these last 2 steps. So why do we need the propagation, and why do we need to defer detection of use of uninitialized memory to sensitive operations? Can't we just raise an error when we load uninitialized memory? Well, the problem is that loading uninitialized memory is allowed as long as its content is not used. This is the example, the case, for example, for compiler optimizations like load widening, where more bytes than needed are loaded, but the code then has to discard the uninitialized portion of memory before using it. The state-of-the-art solution to detect this kind of errors is called memory sanitizer, or MSan for short. It is a compile time solution, and it has a slowdown that is in the range of 2 to 3x. It is very accurate thanks to having access to compile time information, and it is fuzzing compatible. On the other hand, MSan requires the compilation of the whole code, and this means the whole user space stack, including all the libraries that the application needs at runtime. This makes MSan not very fuzzing friendly. Because of this, MSan was disabled a few years ago in the OSFUZ project due to an update to the operating system version in the backend. And as of today, more than half of OSFUZ project, of C and C++ OSFUZ project, have MSan disabled. So MSan works like that, and like this in the example we saw before. So at first, the variables are, the memory for the variables is allocated, but they are not initialized. So the shadow memory is fully uninitialized, and we have, in general, no way knowing what's going to be in their memory. Then the read function is called, let's assume that it successfully reads 2 bytes, and so the shadow memory of the first 2 bytes of buff is initialized. Then the first byte is copied into A, which means that now also A is initialized, and then A's shadow is checked. In this case, it is initialized, so no need to raise an error. We can keep going. Now, since MSan has these issues, it requires the recompilation. You may wonder if we can do UUM errors detection at the binary level. And the answer is that yes, we can do that. And the workflow is very similar to MSan, so we still need the propagation, and we still need to check shadow memory at sensitive operations. These approaches are, we can say that, are more generic in the sense that they can instrument broader variety of software, including closed-source software, because instrumentation is not inserted through recompilation, but it's inserted at runtime. On the other hand, they are much slower. The slowdown is in the range of 10 to 20x, and they have no fuzzing compatibility. This means that we are missing bugs in closed-source software, and in general, we don't have a more generic solution when MSan fails or where MSan's constraints are too much for our application. To tackle this issue, we propose a new approach called QMSan. QMSan is a binary-based multi-layered solution to detect UUM errors. It is based on the QEMU emulator and it is fuzzing compatible, in particular with the AFL++ fuzzing solution. It has three main components. The first one is an accurate detector. This is similar to existing binary UUM error detectors like Valgrins's memcheck or Dr. Memory. It is very accurate, but it is also very slow. Then it features a runtime module which supports UUM detection with shadow memory management. And finally, it features an opportunistic detector, which is a new UUM error detector. It is very fast, but it is also very inaccurate. In particular, it has, as we will see shortly, lots of false positives. The idea behind QMSan is to use the opportunistic detector on the vast majority of the runs, since it is faster, and only use the accurate detector to validate real UUM errors. Now, QMSan's workflow is as follows. We run the program under testing inside the opportunistic detector, and whenever we detect a load of uninitialized memory, which we call a violation, we check it in an ignore list to see if this violation is already known and then safe. If it is, we can resume the execution as if nothing happened. Otherwise, we have to check it with the accurate detector, which means that we are going to replay the execution inside the accurate detector. And the accurate detector will tell us if this was a false positive or not. If it was a false positive, then we add the violation to the ignore list and we keep going with the fuzzing. Otherwise, we raise an error because we successfully detected a UUM error. The key intuition behind the opportunistic detector is that most loads of uninitialized memory are safe, so we don't need to pay the extra cost of expensive instrumentation every time. We can just check them the first time and then use inexpensive instrumentation the next time we see them. So the opportunistic detector only checks memory accesses, both read and write operation. When it detects a write operation, it initializes the shadow memory of the target, while when it reads, we check the shadow memory of the target. If it is initialized, we can keep going with the execution because we cannot have a use of uninitialized memory if we are reading initialized memory. Otherwise, if we are loading uninitialized memory, we have a violation. And when a violation occurs, we can have two cases. The first one is that the violation is known, so we can keep executing. We have already checked that violation, no need to perform any other action. Otherwise, that violation is not known, and we need to use propagation to check it, but we will remember it for next time, so that next time we won't pay the extra cost. Now, this setup requires an ignore list, and we have to be careful while using an ignore list, because if we use policies that are too shallow to add violations to the ignore list, we risk of having false negatives. So QMSan has has one policy that considers three properties when adding violations to the ignore list. The first one we consider is the address of the instruction that triggered the violation. This, unfortunately, is not enough because instructions that trigger violation can sometimes result in UUM errors and sometimes not result in UUM errors depending on the context. So because of this, we take also into account spatial locality, which is the calling context when violations happen, and temporal locality, which is the sequence of violations. We found these three properties to be able to characterize well enough violations to not have false negatives in practice, which we did not observe during our evaluation. Speaking of evaluation, we assembled a dataset of 9 closed-source binaries that are common fuzzing targets for binary fuzzing papers, and 10 open-source programs from OSFUZZ. We selected these 10 open-source programs as not being currently fuzzed with MSan on OSFUZZ and as being among the programs that have the highest count of security-related bugs found during OSFUZZ fuzzing. In the end, we found 27 bugs in the 9 closed-source binaries and 17 bugs in the open-source projects. Then we also evaluated QMSan for performances, and we assembled another dataset of 8 common fuzzing benchmarks from Google Fuzzer Test Suite. The reason we needed another dataset here is because we needed to use projects that are also compatible with MSan. So we detected a final slowdown which is 1.51x over QEMU AFL, and compared to compile time MSan, it was 1.55 times slower and 3.75 times slower than AFL compiler, so compiler instrumentation. So in conclusion, we can say that detecting UUM errors is a challenging task, and we presented a new design that drastically limits the cost of instrumentation at the binary level. We detected 44 new bugs, and 4 CVEs were issued as a result. This is the link to our GitHub repository where you can find the code and all the necessary data for the evaluation and reproducibility. That would be all. Thank you.
Thank you. Do you have questions from the audiences? Yes.
Thanks for the talk. Very interesting, and I really loved your work. I have a question about the ignore list. So you talk about spatial locality and the temporal localities, right? To figure out whether you want to trace that load again or not.
Sorry, can you repeat the answer?
You talk about spatial locality and temporal locality. I wonder, do you also take in consideration register values or other memory values around that specific address?
No, we did not. We tried during the early development taking into account other memory, the memory status and also the memory object, but we were having like too much noise, and the result, it was we had an explosion in the amount of executions we had to run in the accurate detector, and so basically we're only using the accurate detector, which was pointless. So.
All right, thanks.
Thank you for your question.
Palmer Young from DoD. Have you tried to use your QMSan against other architectures such as MIPS, ARMS, or any other architecture other than QEMU?
Oh, another architecture?
Yes, sir.
Okay, yes. So thanks for your question. Yes, we did. Since it is based on QEMU, we can use it on other architectures. In particular, we did some experiment with x86. With ARM or other than x86, and we succeeded. We detected the same bugs on the binaries we tried as we did for x86, and we did some testings with, particularly with the NVIDIA binaries. We detected the same bugs with similar TTs. There are a few details about this on the paper. Thank you.
Yeah, that actually triggers me interesting question. I mean, if you go to some sort of those ARM-like those architectures, the memory model is different, wing memory model. So you may need to emulate those behaviors. Sort of the load is the sort of the switch, the order is out of order machine. You understand what I'm saying? So what I mean is that it would be very different from the x86.
Okay.
Because the memory order can be changed.
Oh.
Very aggressively in the weak memory model.
Okay, yeah.
That can be some. I have another questions about. So looking at the performances of your system, so it seems not really that different from the MSan. And so what I mean is that so my question is, what's the sort of the advantage of the QMSan compared to the MSan?
Well, we can target more software than MSan does because we can target closed-source software, and in addition, we don't require recompilation. So we don't need instrumented libraries. We don't require the whole user space stack to be recompiled. So it's more of a plug-and-play solution, other than being able to target a wider class of software.
I see.
My last question: have you tested against BooFuzz, and does it have to be source code, or can it be compile executable, or when fuzzing?
Tested against?
BooFuzz, BOOFUZZ. BooFuzz.
No,
you haven't heard of
we
BooFuzz?
didn't.
Okay. And then for fuzzing, does it have to be source code, or can it be a combined like executable F file? Or
okay, no, in general, it can be binary fuzzing. This is supposed to target binaries. Then, of course, you can compile it and then run it.
So our author is strong. He can answer any question. Yeah, let's thank our speaker again.
Thank you.